So last chapter that we're going to take a look at is chapter 11. Chapter 11's got a few different topics in it. The first two sections are on what we call sequences. That's the first section. And then a series. That's the second section. So a sequence is basically a list of numbers. And the goal is going to be to find formulas that can predict the number in the sequence. So for short sequences, we can usually figure it out. But let's say we had a sequence and I said, what's the number in the 3,407th spot? We don't want to have to try to figure that out by hand. Okay, we want to have a formula. So basically, a sequence of numbers is a set of numbers that have a specific order to them. A lot of times we will name a sequence using a lowercase letter. And then each term in the sequence has, if you want to identify it, you use the name of the sequence and you put a subscript number. That subscript means what's the number in position 2 of sequence B. In this case, it's 1/2.
And that one would be easy to solve for any number, really.
Yeah, the formula is basically just 1 over n, where n is the position number. Yeah. So that's a pretty easy one to figure out. So the 500th number would be 1 over 500. Yep. But one thing to notice here is that there is no ... at the end of it, which means this sequence has a stopping. I don't know what the stopping point is as a number, but I know it stops at n. That is the very last number in the sequence, 1 over n. If you see a ... after something, then that means there is no end. Okay, that's called an infinite sequence, and it goes on forever. So we're going to talk about infinite, which goes on forever, and finite, which stops. So in order for a sequence to be unique, like not the same as something else, there has to be some rule for calculating the terms of the sequence. If you have what you think are two different sequences, but they use the same rule for finding terms in the sequence, then they're the same thing. They're not different. You might think by starting at a different spot, it's different. Like if I gave you, let's say, the sequence like that, and I started at number 1 versus somebody else starting at number, well, let's say you started with just this part. Well, if this sequence that's in the box starts at 1, you'd have to work backwards to figure out what the first 3 terms are by looking at the pattern that you see. So it's multiplied by 2 as it gets bigger. It's divided by 2 as it gets smaller. So if these 4 numbers I said were part of a sequence that started at 1, then this is really your sequence. Right? So whether you know the first term or you don't, if you can work backwards and figure it out, it might end up being the same as another sequence. So you always want to make sure you know where your sequence starts, and that's the best way to compare 2 sequences. If you know where they both start, and then you find a formula, then you can see if they're the same sequence. Okay, so here's a sequence, and I want to see if we can figure out the pattern for it. Okay, this would be a sub 1, a sub 2, a sub 3, and this is a sequence that goes on forever. Does anybody see how I could get any term that I want to know specifically? Yeah?
As an equation?
Yeah, I'm looking for a formula.
You can do 2 plus 3t times n with, or 3n, just do
3n
plus 2.
plus 2.
Because you started 2.
right, let's try it. Okay, so what this formula is saying is that n is the position. You triple that, and then you add 2. Well, let's try it for the number in the first position. If you triple 1, you get 3. And if you add 2, you get 5. So does that formula correctly give me the number in the first position? No. In the second position, it would be take the second number. 2 times 3 is 6, plus 2 is 8. We're kind of off by 1. So what could I do? Yeah?
That would just be 2n plus 1.
Well, if we try that, I don't think that's going to work either.
I thought it was just adding 3, but I think I could multiply something first.
Anyone else have a guess what the formula would be? Yeah?
3 times n minus 1 plus 2.
Okay, so now that's kind of looking at a different approach. I do want to come back to that. So you said 3 times n minus 1 plus 2. All right, so if we simplify that, we essentially get 3n minus 3 plus 2, which is 3n minus 1. Let's try it. So this formula says if you triple the position number n minus 1, you should get the term you're looking for.
Yeah.
Well, if you triple 2, you get 6, minus 1 is 5. Okay. If you triple 3, you get 9, minus 1 is 8. If you triple 4, you get 12, minus 1 is 11. Yep. So that is one way to write a formula for that sequence, 3n minus 1. There's also another way. That's the best way. There is another way. What's the pattern here? Adding 3 to what?
The previous number.
Add 3 to the previous number. So if this is the term that I wanted to know, a sub n, what's the one before?
A sub n minus 1.
Yep. So that's the one before it. And Jess said to add 3. That works as well. So, for example, if you want to know a sub 3, that means you take a sub 2 and add 3. So if you take a sub 2, it's 5. And if you add 3, you get 8. But I don't like that one as much. What do you think I don't like about that one?
It has you know your start.
Yeah, what?
You know your start, right?
If they're going to give you a sequence, they would tell you where it starts. They'd give you what's on the board right here.
Oh.
So you'd know it starts at 2. So that's
They
okay.
have to give you a position to start with to add to get the number.
Yep, and they will. They'll give you what's on the board right there.
Well, like with AN, we said it was 3, but it could be like 64. You'd have to know what a sub 63 is to add 3 to.
Okay. And then how would you get a sub 63?
That's the thing, you'd have to go all the way back. It just takes too long.
Yeah, if you use a formula like this, it's called recursive, you have to know every single number up to the one that you're looking for.
Yeah.
Because to get the 70th one, you need the 69th one plus 3. But to get the 69th one, you need the 68th one plus 3. So you're going to go all the way back to the beginning. Versus a formula like this, if you want to know the 70th term, it's just 210 minus 1. So I can find that very quickly without worrying about anything that came before it. So this type of formula is called recursive. This one is called explicit. Explicit is much better.
Recursive?
Recursive.
Okay.
Yep. Well, I'm gonna write those down. Okay. And we're gonna talk about how can you figure this out. Like this 3 times n minus 1 plus 2. That's a special formula that you can use to figure out a pattern if the pattern is adding a number each time on a sequence. So we'll come back to that. So you're not just going to have to kind of guess. Is it like triple a number and minus 1? There's going to be kind of a way to figure this out. So essentially a formula for a sequence, it's like a function. You plug in a value and you only get one value back from it. There's only one number in each position. But when you think of a function, you can plug in anything usually for x. Positives, negatives, fractions, decimals. Well, when you think of a formula for a sequence, the domain is just positive integers because the domain represents the position of the term you want to know. There's no such thing as what number is in the negative fifth position. Positions start with 1. That's the first position in the sequence. There's also no number between position 1 and position 2. There's no such thing as 1.5 position. Okay? You can't do that. So when you come up with a formula for a sequence, the only values you are allowed to plug into it are positive integers. Nothing else really would make sense. Any question on that? So an infinite sequence is a sequence that goes on forever. And the numbers that you are allowed to plug in to the formula for that sequence would be the entire set of positive integers from 1 all the way to infinity, including every number. That's for an infinite sequence. Now, a finite sequence stops somewhere. You might not know where it stops, but as long as you know that it's finite, that means that the numbers you are allowed to plug in from the formula, they start at 1, and they go up to some value. Could be 10, could be 1 million, could be 50 million. But the point is the numbers stop somewhere. So you'd be allowed to plug into some formula, which we don't know, every number from 1 up to that integer right there. And that would be the end of your sequence. So just because a sequence is huge doesn't mean it's infinite, even if it has billions and trillions of terms. If it stops somewhere, it's still finite.
So what were you saying about the slide before with everything has to be integers?
The domain is always positive integers for a formula for a sequence.
Okay, was that like n with 1?
Yeah. So you can only plug in positive numbers because it doesn't make sense to go to positions before the first one. There is nothing. And it doesn't make sense to try to find a position between two positions because there isn't one. All right, so here's some examples where they give us a formula and they just want us to find the first 3 terms and the 15th term. That's an explicit formula. So you can jump to finding whatever term you want by filling in whatever number you want for it. So that's a good formula. All right, let's start with the first term. What would I plug in for n to get the first term? Yep, plug in 1. So when I plug in 1, what am I going to get in the numerator?
0.
So I'm going to get 0 divided by 1, which is 0. So the first term in this particular sequence is 0. Let's do the second. Right, so we're going to plug in 2. What do we get in the numerator? So 3 over 2. So 3 halves. All right, let's do the third term. What do we get there?
8 over 3.
So we get 3 squared is 9 minus 1 is 8 over 3. And how about the 15th term?
Over 15.
224 over 15. Now, there might be a value that this is approaching. Okay, we're going to talk about that too. And there is. It looks like it might be getting closer and closer to something. Like this number in relation to this number. And if you look at it carefully, when n starts to get really big, does this -1 make a difference really?
Not really.
No. Like if n was 1,000,000 and you square it, what's the difference between 1,000,000 squared and 1,000,000 squared minus 1? Not much. So essentially what you're doing is this. When n starts to get really, really, really big, which simplifies to what?
Just n.
Just n. So what's happening in this sequence is as you get bigger and bigger and bigger and bigger, the value of the term approaches the position of the term. It's not quite. It's always going to be a little bit off. But this is very close to the number 15 if you divide it out. It's probably going to be like 14.99 or something. But the bigger and bigger and bigger you go, the closer and closer the value of the term gets to its position in the sequence.
14.93.
14.93. So even just going to the 15th term, this is almost 15. It's 14.93.
Wait, so what exactly approaches, like, so just A of n approaches n? A sub n?
Yeah, A sub n approaches n, but never quite reaches it.
Yeah.
Never quite, because of that -1. All right, let's try this one. So what's going to happen? Does anybody notice before we start doing it what a characteristic that this sequence is going to have?
Like besides the n being exponents?
Well, it's something special is going to happen in this sequence. It didn't happen in the last one. Anyone think they see something that's gonna happen?
Are we
So you're gonna alternate
That's
between
gonna
negative and not negative.
Yeah, this is what we call an alternating series, alternating sequence. An alternating sequence alternates positive, negative every other term. So that's all that -1 to the n is doing. That's just alternating. And then the 2 to the n is doubling. So it's going to double each time and become the opposite. That's what's going to happen. So what do we get if we plug in 1 for our first term? What's -1 to the first? -1. And 2 to the first? 2. So we get -2. Second, what's -1 squared? 1. And 2 squared? So it's going to double each time and become the opposite. So what's the next one? -8. Now, to get all the way to 15, I mean, we could figure it out. We know the odd ones are going to be negative. So it's going to be a negative. And I could just double it until I get all the way to 15. Or just use the calculator and figure it out. So we know it's negative. And 2 to the 15th power is going to give me 32,768. The other downside with trying to double it each time is if you accidentally press something and do it wrong, it's easy to make a mistake. Especially if you had to double it to say, forget 15, maybe 150. You just want to plug it into the calculator and not have to worry about doubling each time. Any questions on that?
Is there a button on the calculator to double your answer, or do you have to hit ×2 every time?
Well, once you do ×2 once, you can just keep pressing
Yeah,
enter.
Oh.
But still, it just, you want to come up with a better way. It's going to be that many times. Okay, so again, because a sequence of numbers is basically like a function, except the domain is only positive integers, we can graph a sequence. The only difference between graphing a sequence and graphing a function is continuous. When you draw your function,
Is what?
continuous. You draw a line that's connected. When you graph a sequence, it's just certain points. It's not connected because there's nothing between the first and the second value on the x-axis. So it looks like dots. All right, so let's try that on this one. This is the sequence that we already did. Probably not going to go all the way to 15 because it's going to be off my grid a little bit. But what did we get for the first number in the sequence? 0. So the way you graph that, 1, 0. There is no number on the 0 on the y-axis because there's no such thing as the 0th position. It starts with 1. What did we get for the second one?
3 halves.
Second one was 3 halves, so that's like 1.5. And you don't connect it. Connecting it would mean that there's more data between those two, and there isn't. There's the number in the first spot and the number in the second spot. And that's it. The third spot was what? 8/3. 8/3. So what's that? 2 2/3? 8/3. And 2 2/3. Yeah. So what is 2.7? So 3, about 2.7. And what's going to happen is each time you go over, your dot is going to get closer and closer and closer to that line because it's supposed to be approaching the value. So it's almost like y equals x when you start to get to real big numbers. If we did one more, we'll do the fourth one. 4 squared is 16, minus 1 is 15. And 15 divided by 4, what's that give? 3.75. So 4, 3.75, even a little closer. And that's what the graph of a sequence looks like. It's just dots. Any questions on
line?
What's that?
The function would be a line connecting over.
Well, if it was a function where the domain was all real numbers, then yeah, you'd be able to connect it. But the domain here is only integers, so you can only put a mark at each integer. And then you can start to do some interesting things with sequences. You can like map a sequence to like musical notes and see how the sequence sounds. So you got to figure that part out. But if you map the numbers to notes, then sometimes you start to get some sequences that sound kind of neat. And there's a website that does that. Map sequences to notes.
You show us.
Sure. If we have time after, I can show you. Yes. Yeah. A lot of times it just sounds real random. Just like it doesn't sound like anything. It just sounds like somebody pressing random notes on a piano. But sometimes if you find the right sequence, you can get one that actually sounds like something. So the formulas that we used in the last two problems, the n squared minus 1 over n and the negative 1 to the n, those were called explicit formulas. Explicit formulas are the best formulas to work with because you can find any term of the sequence that you want directly. Another kind of formula is recursive. Recursive is usually easier for somebody to think about because to do recursive, all you have to do is say, okay, what did I add to the one before it to get the one I'm at now? So that's usually an easier pattern to come up with, but unfortunately it's not very useful. Because once you get to numbers that are really high, you have to use a recursive formula, probably going to make a mistake. So in a recursive formula, since it always depends on the one that comes before it, I have to give you at least the first couple terms. Okay. You could even have a recursive formula that does something like this. What would that mean if you had a recursive formula that looked like that? How would you explain what's happening here? Yeah?
It's 2 times the sum of the 2 numbers in the sequence before.
So it's not that. That's what you said.
Oh, okay. So it's 2 times the number that was 2 previous in the sequence.
Yep.
Plus the previous one.
Yeah. So this is a recursive sequence that goes back 2 spaces. It doubles the number that came 2 before it, and then adds the one that came directly before it, and that's how you get the next one. So if I wanted you to come up with a formula like that, which would be pretty tough to figure out, I would have to give you at least the first 2 or 3 numbers in the sequence so you could start to see a pattern. If I just gave you one number, you wouldn't be able to figure it out. Even if I gave you 2 numbers, you couldn't figure it out. I'd have to give you at least 3 or 4.
Wouldn't this like not work if it was like an even number of things? Because wouldn't like to find the second term when you, or would you just use 0?
Well, the second term would have to be given to you. There's no way that you could do, like if I did this and then this, now you can go from there. This formula would only work to start calculating the third term and on.
Okay.
You can't calculate the second term,
because it takes.
and you can't calculate the first term because then you can't go back that far. So in a recursive sequence, they have to give you as many positions as the formula goes back when it references. Yeah. But yep, you could use these 2 and then build a sequence using that. Double this one and get 6, add 8, and then put 6 plus 8 right here, and that's your next term. Okay, so recursive formula, the first few terms are given, and you figure out the next one based on what came before. And there is a way to turn a recursive formula into an explicit formula. We're going to look at it for some basic ones, but in general, turning a recursive formula into an explicit formula isn't always that easy. It can be very hard. Extremely hard. Depends how complicated it is. Okay. So here's an example of a recursive sequence. And this particular recursive sequence only references the one number that came before it. So I only need to start you off with one number. So based on that formula, what would be the next term in the sequence?
5.
Yep. And then 8. So it basically just says to take 3 and add it to what came before. Now, if they didn't start you off with any number, then you can't use this because you don't know what to start with. Any question on that? Okay. So it says determine the first 4 terms and the 8th term of this. And it's a sequence that's been defined recursively. So unfortunately, to get to the 8th term, we're going to have to get to every number, every term that comes before it, even if we don't need it. All right. So what's the term in the first spot? 2. How do we know that?
Because that's A1.
Yeah, that's given. All right. So now, what would be the term in position 2?
6.
And 3?
10.
And 4.
14.
Okay, so that answers the first part of the question. Determine the first 4 terms. But to get to the 8th term, we really have to continue the pattern. So 14,
18, 22, 26, and then 30.
So that wasn't too bad because we only had to go up to 8. But if we had to go up to, say, 8 million, well, we want to come out with a better way to do it. So that answers the 8th term, and that answers the first 4. Okay. Questions on that? All right, so now let's see if we can take something that's recursive and turn it into explicit. In general, I told you, the ones we do it with are going to be pretty easy. They're not going to be tough ones. So the easiest way is probably to list the first 2 or 3 so you can see the pattern and then kind of go from there. So let's just list the first 3. What would your second term be? 8 in your third term? 13. So that's probably enough to test your formula on. You can go one more if you wanted. But the goal now is to find a connection between what can you do to the number 1, that's the position number, to turn it into the value 3. You could say, oh, well, I just add 2. Well, the trick is you have to make sure that adding 2 to the position number works every time. So it's not add 2, because somehow I go from 2 to 8. You might say, oh, okay, well, I'm going to try times 4. 2 times 4 gives me 8. But 1 times 4 doesn't give me 3. So, does anybody see what the pattern is? Yep. Yeah, it is times 5 minus 2. And if you're like, well, how do you figure that out? I'm going to show you. But the 5 has something to do with the fact that you are adding 5 each time. Let's try it. What's 1 times 5? And then minus 2. 2 times 5? 10. Minus 2? 8. And 3 times 5 is 15. Minus 2 is 13. So it seems like it works. Now, the real question would be, prove it works. You can't prove that this is actually true by just showing it to me a bunch of times. To prove that it's true, we could use something called induction. Okay, that's in section 11.4. It's not something that we're going to learn, but it's a way to prove these kinds of statements. Right, let's look at this one. So this is a pretty popular cursive sequence. And it's a specific type of what we call a Lucas sequence. And the idea of a Lucas sequence, at least if I remember right, is that you take the 2 terms that came before it and add them together. If those particular 2 terms start with a 1 and a 1, then that Lucas sequence is called a Fibonacci sequence. So the formula is add the previous 2 terms together. Now, this is seems like a pretty simple formula, but if you wanted to convert this to an explicit formula, so that way I could say what would be the 942nd Fibonacci number. Well, that's actually very hard to do. At least that we don't have the math at this level to even try to figure that out. It's a little complicated. I did it once. I don't even remember how you exactly do it. But luckily we don't have to do it.
Fibonacci's a mystery.
Yeah. So what would be your first 6 terms, starting with, well, the first 2 are given, 1 and 1.
1, 1, 2,
2.
and then 3, and then 5, and then 8.
And that's it. Just the first 6.
Okay.
Yep. 1, 1, 2, 3, 5, 8. So if somebody said to me those numbers, 1, 1, 2, 3, 5, 8, I would recognize them as the Fibonacci sequence because anytime you write the Fibonacci sequence, you always start with 1, 1, and you go up. Well, if somebody gave me numbers in the hundreds or thousands, I wouldn't recognize them as Fibonacci numbers because they're so big. Normally, when I write the Fibonacci sequence, I never go that high, which is why when I was doing an escape room, and the back of the paintings had Fibonacci numbers on them that were in the thousands, I didn't recognize them as a Fibonacci sequence, and we didn't get out of the escape room because I didn't recognize the Fibonacci sequence.
No, escape room.
But I don't blame myself because I don't know Fibonacci numbers in the thousands off the top of my head. So I guess I could have figured it out, but I didn't.
Where was the escape room?
I won't tell you. I won't ruin it.
Where was the escape room?
Well, somebody might want to try it, and then they'll know how to do it.
Come on.
So,
They won't remember.
anyway.
I won't remember.
So,
All we know is
that's the Fibonacci sequence. Okay? And you could spend like a month, and there's all kinds of things about this sequence, all kinds of patterns, places you find these numbers. We'll look at something in 11.3.
Yeah, there's like a lot like in nature, right?
Yeah.
Like flower petals, right?
we'll look at something called Pascal's triangle, and I'm going to show you in Pascal's triangle how these numbers come up in it. They come up all over the place.
Isn't there also that spiral thing that shows up in nature all the time?
Well, actually, I'm going to show you right now.
That's from the Fibonacci sequence.
Yeah, I've seen the spiral thing, like a nautilus shell. I'd have to see. I'm not 100% sure what the sequence is there, but it might be. Might have something to do with the golden ratio too. I don't know. Golden ratio comes up different places. That's something else. So that Fibonacci sequence can actually be found in this triangle. We're going to look at this triangle next week when we do 11.3. But the idea in this triangle is that if you take any two numbers above, add them together, that's how you get the number below. It's always ones on the outside, and then like 6 plus 15 is 21. 10 plus 5 is 15.
That's pretty brilliant.
Now, what's interesting, a couple things there's a lot of things interesting about this triangle, but one thing that's interesting is if you go to a prime row, like 5, every number in that row is a multiple of that row number. So row 5 is all multiples of 5. It's always ones on the outside. Row 5, 6, 7. Row 7 is always multiples of 7. That wouldn't work for row 8 because that's not prime, 9's not prime, 10's not prime. But row 11 would all be numbers that are multiples of 11. 5, 6, 7, 8, 9, 10. I don't think I have 11 on. So I told you I'd show you where the Fibonacci numbers come up. And if you take this and put it, I always forget exactly how to put it. Well, let's try it. Let's try it there. I'm trying to just line it up on the diagonal the best I can. If you add up the numbers on the diagonal, okay, so let's just see what happens here. Actually, let me move it up. I think I do want it up here. Uh-oh, not that though. I want to move it all together.
What'd you do?
I don't know. It's not together anymore. Now it is. Let's try it. Well. Okay, well, I can just add one. I can just go like this. There you go. That's what I want. All right, so let's add up all the numbers that it goes through. It doesn't count if it hits the edge of a hexagon. It has to go through the middle of it. So look at the first one. What number does that first line go through?
1.
Just a 1. All right. How about the second one?
1.
It's just a 1. Remember, we're adding them up now.
Oh, that's weird.
Look at the third one. 1, and it goes through a 1, which is a 2. And then this one goes through a 1 and a 2,
That's 3.
which is a
That's
3.
crazy.
We'll do one more. A 1, a 3, and a 1. 5.
It's
So,
the Fibonacci sequence.
yep. So if you look at those diagonals in Pascal's triangle, you get the Fibonacci sequence. So yeah.
Did not just say
This is some pretty weird stuff, Mr. Hager.
Yeah, so
Look at that. That's literally
It does go
the
to
Illuminati is hidden in this.
I do have the numbers that are multiples of 11 right there. Yep. Okay, so let's look at the last two kinds of sequences for today. A lot of times a sequence isn't only described by how many terms are in it, that's using finite or infinite, but you can also describe it by the pattern in the sequence. If you have a sequence where you add the same number over and over, that's called an arithmetic sequence. Okay, an arithmetic sequence is a sequence where you add to get to the next term. And the idea is if you write it recursively, it would look like this. To get any particular term, take the one that came before it and add some value. So the next term is always the previous term plus some value. And the reason we use the letter D is because D is called the common difference of the sequence. So you might be like, well, wait, you said you're going to add to get from one term to the next. Why are we talking about a common difference? Well, look at this.
It's 2.
The idea of a common difference is you take a term, subtract the one that came before it, and see what you get. If you get the same thing every time, then you have an arithmetic sequence. Okay? So 13 minus 11 gives me how much? 2. 11 minus 9? 2. They're all going to come out to 2. So this sequence has a common difference of 2. As long as we know what the common difference is, and we know what the first term is, we can very easily come up with a formula for this without trying to guess. So,
if there is a common difference, it's an arithmetic sequence.
yep. So if I wanted to come up with a formula for this, what I usually do is I put the position numbers above it, and then I see, is there some way I can turn the position number into the term? And yeah, let's just double it and add 1. So is there a way that we could figure this out if you couldn't just kind of look at it and do it in your head? And the answer is yes. It's going to depend on the first number that you see and the amount you add each time, which is the common difference. And here is the formula to do it. This is the first term. N minus 1 is something that always stays the same. And D is the common difference. Now, it gives you something that you need to use the distributive property on and simplify, but it will give you the correct answer. So let's try it. What was the first term in the sequence up there? 3. And what was the common difference? 2. What do you get when you distribute the 2?
2n minus 2.
2n minus 2. And combine like terms?
2n plus 1.
2n.
Which is the same thing.
Plus 1. So this is a formula that we can use to figure out a formula for arithmetic sequences. So it only works if you add the same number each time. And of course, n here represents the position number, and position numbers have to be positive integers. Can't use fractions, decimals, 0, or negatives.
What does the T mean?
The T?
The middle spot. It looks kind of like an E.
Oh, this means n is an element of the positive integers.
Oh,
That's the symbol for element of.
I get it, because it's like an E and an O.
Yep.
Wow. It's really
It's supposed to look kind of like that. Okay, let's try this. The way I gave it to you, it wasn't doable. I have to give you the first term. So, in the past, the way I would have said is, all right, write out the first few terms in your sequence, see if you can figure out the pattern. Let's just jump right to the formula. What's the formula that we just wrote down for an explicit sequence?
A prime plus parentheses n minus 1 times e.
Now, let's fill it in. What's my first term? 5. And what's the common difference in this one? It's 3. That's what you're adding to get from one term to the next. Okay, so simplify that, and you're going to get, what, 3n plus 2. Yep. And if you want to check the pattern, well, you could write out the first few terms based on that formula, and then see if it matches your formula. So like you'd have 5, 8, 11, 14. Check the third one and see what you get. What's 3 times 3?
9.
Plus 2? 11. So does that prove the formula? No. But if you check it and it works for 3 or 4 of them, then you're probably okay. Proving it is a whole nother thing. Okay. Any question on that one? Okay, so adding each time, that's an arithmetic sequence. Let's take a look at another one. It says the first two terms in an arithmetic sequence are -8 and -2. Find the fifth term. So let's say they also wanted to know the formula, because I probably would ask for the formula on a test. What's your first term? And what is your common difference? Adding 6 each time. So, let's write it up here, and then we'll write the simplified version down here. What's going to be my my rough draft of my formula? Yep. M6. And when I simplify that, I'm going to get 6n
Is finding it explicit?
minus 14. Okay. Now, whether they want the fifth or the 5,000th, it doesn't make a difference. We just fill in n. So what's a sub 5?
6 times 5. 16.
16.
My math is a little slow.
Okay, so again, not that you need the formula to find the fifth one here. That wasn't that far away, but they would probably ask you to find it, and they may give you one that's a lot further than 5. Okay, questions on that?
I was 16.
All right. So this one says to find an arithmetic sequence, but what are you missing that you need?
The first term.
Yeah, you don't know the first term, and you don't know what you're adding each time, or subtracting, or whatever it is. But just because you don't know what you're adding or subtracting each time, you should still know something about kind of the hop that you take each time.
Wait, was it?
It's going down in value.
It's going down, and what else do we know about the amount it goes down each time?
It's the same.
It has to be the same. Okay, so you just have to figure out, I mean, it's not that big of a difference from 13 to 3. You're either going down by 1 each time or 2 each time. It's probably something like that. You're going down by 2. So that would give you 11, 9, 7, 5, and 3. So to write an arithmetic formula, we need the first term. Well, let's just work backwards. So what's the second term?
15.
And the first term?
17.
Okay. So what would be my formula? We can kind of write it, how we would first, and then we'll simplify.
17 plus n minus 1 times 2.
Times 2. So what's that going to give me?
2n.
Yep.
Plus 15.
Plus 15. And it's easy enough to check. Let's check the third term. 2 times 3. Okay, I see what we did wrong.
Uh-oh. What happened?
Why? What did we do
Is
wrong?
it minus 2?
Yeah, it's
Yeah.
fine. Because we're going.
Such a good
Minus 2. So it's going to be minus 2n. And then what's going to be my constant?
19.
19. All right. Let's try this.
There.
Check the third term. -2 times 3 is -6. -6 plus 19 is 13. Okay. So it's always a good idea to check at least one of them the way I just did, because you might catch a mistake. Questions on that one? Okay. So I think that's pretty good for an arithmetic sequence or arithmetic progression. Same thing. Does anybody know what a geometric sequence is?
That's the
Isn't it
multiplying, isn't it?
multiplication?
That's how you multiply, yep. So in this type of sequence, you get a term by multiplying the previous term by a constant. This would be kind of like, if you were to think about it in terms of Algebra 1, this is an exponential sequence. Anytime you multiply it, like if you double each time, it grows exponentially. So this could either be like an exponential growth or decay kind of thing. So the idea here is to get a term, you take the previous term and you multiply by r. Now, last time the variable we used was a d. D represented common difference. This has to do with a common ratio. So if you think of, well, what do you mean division? We're talking about multiplying each time. Why is r a ratio? Well, think of it like this. That's a geometric progression, okay, or sequence. To find the common ratio, take any term you want and divide by the one that comes before it. And what do you always get in this case? 2. So the common ratio is any term divided by the one that comes before it. And there's different ways you can write it. The idea is the top one has to be 1 later than the bottom. And that's your common ratio. And there's a formula to figure this out as well. The formula is a sub n equals your first term times r to the n minus 1. So let's try it on the sequence I just did in red. What was my first term? 3. And what was my common ratio? 2. So what could have been a little kind of tricky to figure out, like with exponents and what your formula is, becomes pretty trivial. So the formula is 3 times 2 to the n minus 1. Let's check the fourth one. What's 4 minus 1? 3. What's 2 cubed?
4.
8 times 3?
24.
24. There you go. So this is the formula to find the nth term in that sequence. Any question on that one? So each formula depends on 2 things. Well, they both use the first term. One of them uses the common difference. The other one uses the common ratio. And if you don't have a common difference or a common ratio, then it's not arithmetic or geometric. For example, the Fibonacci sequence. It's not a common difference. It's not a common ratio. Neither formula would help you in this case. So there are formulas that don't fit into either one of these patterns. And then it's a whole other method to try to figure out. All right. So the homework, I think I can just change this. There we go. So 1 through 13 odd. 14 is the only even question. 17 to 27 is odd, and then 31.
What unit number is this? 11.2?
This is 11.1. Tomorrow we'll do 11.2, part 1, and that'll be it for this. Thursday is a review day.